Okay, space students, or space science students, it's an attempt at a video lecture on erosion, weathering, and sedimentary rocks. Yeah, it's a good one to do in preparation for our field trip next Tuesday. So yeah, we're talking about sedimentary rocks, and when I do that, really I would be remiss if I did show you at least one picture of the Grand Canyon. Of course, pictures don't do it justice. If you've been there, you know that. You've simply got to stand on the edge and just look at that, and it just makes you quiet. It's just so very impressive. But of course, it's not alone. Some other features nearby is Bryce Canyon. It also has its own spectacular nature. Some cool sedimentary rock pinnacles there. Remember, sedimentary rocks are made by pieces as weathering knocks pieces off pre-existing rocks, transports them somewhere, deposits them, and then by some process reforms them into sedimentary rocks, into new rocks. So these pedestals, these pinnacles of rock are made of pieces or parts of other rock that were transported to this part of Utah and then deposited and formed into what you see after they themselves were then weathered. Other places would include Zion Canyon, right here also in Utah, more spectacular sedimentary rock formations. And then Antelope Canyon, again an Arizona feature, but it's beautiful sedimentary rocks. This is all in the Red Rock region of our country, what they call the Red Rock region, the Southwest. Of course, weathering affects and sedimentary weathering affects many places. This is the picture you would see if you looked at the New Hampshire State Quarter. I don't know if you collected all those state quarters. And this rock formation was called the Old Man of the Mountain, and you can kind of see a pronounced brow ridge and nose and a chin. Unfortunately, it no longer looks like that. After the quarter was made, he fell off. And so here's a before and after of that feature. It's an old, I think it was a piece of granite. There had been many attempts to try to shore up cracks that had occurred in it, but to no avail. And the Old Man of the Mountain's face fell off into a pile of rubble at the base of that cliff. Sad to say. So to start out this then, we're going to be talking about the forces that would be able to do such a thing. And to sort of distinguish erosion from weathering. Erosion, as your notes say, is a generation or removal of rock pieces from their place of origin by, four main forces. Some of them kind of the same thing, different forms of the same thing. Water would be one of those main forces. Wind is another. Glaciers, which is frozen water, or gravity. And just to give you an idea of what that can look like, I've included a link to a 2.5-minute YouTube video of a sandstorm that occurs at the Al Asad Air Base in Iraq. And the first minute or so is just it coming, big winds blowing lots of sand. But then the very end of the video, you can see what happens during the middle of the day to the light. It's just incredible, the force that some of these erosive forces can generate, can utilize in breaking apart not just rocks, but everything. Weathering is really the first step in erosion. There's two types, and we're going to talk about mechanical and chemical weathering. Mechanical weathering really has six main elements to it, six main forces that do the mechanical weathering. And the first one, arguably the most prevalent, is ice wedging. And so if I go to this image here, it's an attempt to show you what ice wedging is. Basically, you got water filling the cracks in a rock and then freezing. And as they freeze, it expands 10%. Remember, water is that one substance that actually gets larger when it goes from a liquid to a solid. It expands in volume. Everything else goes the other way. If it goes from a liquid to a solid, it shrinks, but not water, because the hydrogen bonds lengthen. Okay, and as it does that, then it pries the rock apart. And that rock gets pried apart, and it's largely what's responsible for what you see at the base of mountains. Like this is called talus here, and this would be a talus slope. Here's the rocks that talus had fallen off from. Very angular, not much soil there, just broken rock fragments. That's what ice wedging does. It is arguably one of the main, if not the main, weathering force in this part of the country. Salt cracking would be the next one. And really, salt cracking is the same as ice cracking, except that formation of salt crystals does the work rather than ice crystals. This is more typical in a Mediterranean climate, like around the Mediterranean Sea or in the southwestern part of the United States, where you have water that has a high degree of salt. Now, by salt, I mean anything that is dissolved in water. It doesn't have to just be sodium chloride. And it can be many different salts, magnesium chloride, potassium chloride, lots of different things could do it. But as that water evaporates, the mineral crystals form, and as they form, they expand that rock crack just like the ice does. So it's a similar process, but using a different substance than ice. The next one is abrasion. And abrasion really is like that sandstorm that I was showing you. Those sand particles, basically beating against, driven by the wind, beating against whatever they do is going to really polish whatever they strike. And so that abrasion is a major force. And of course, areas that tend to be drier, that have loose sediment that can be picked up, in this case, Iraq. That's what this video looks like. That's the beginnings of the sandstorm. They're affected by abrasion. Okay. Another good example would be a rock tumbling down a river. And as that rock gets tumbled down a river, it is impacting other rocks and knocking off edges or parts of both rocks, and that also can be a significant abrasion force. Okay. The next one on your notes is organic activity. Organic activity would be like this tree that you're looking at right here. See if I can shrink that down just a little bit. Right in the rock. This is up at Taylor's Falls. We'll actually see this tree on our field trip. You can see here how it's growing right out of the rock. Kind of a tenuous clinging to life, if you will. And then a little farther along the trail, let's see, do I have the next one? No, I guess that's the one that I've got. Yeah, I'll show you another example of this as well. Maybe I have it down lower here. I do, there we go. Here's another one of a tree root that's just clinging to the rock. And as it's doing that, though, it's really prying the rock apart a bit and weathering the rock. Now, it might be chemically weathering, but it's also physically weathering the rock as its roots penetrate cracks and pry them apart. The next one is thermal expansion contraction. And this is a good example. This picture here is a good example of that. This rock was not hit by this hammer to break it. Rather, that rock was sitting out like on the Mojave Desert in the desert Southwest. And if you've ever been in the desert Southwest, you know that during the day it's, of course, very, very hot. But at night it can get really cold. Big temperature swings day to night. And the reason for that is because there's really not much water vapor, not in the air. There's not much vegetation to hold water vapor, and even in the air, there's not much relative humidity. So what happens is a rock like the one you see here, it's sitting out on the desert floor during the day and it's getting heated. As things get heated, they expand. They become less dense and expand. Okay, but then nighttime comes and it gets really cold, and so this rock would contract. And just like a piece of metal that you bend back and forth until it finally breaks, this rock will expand and contract until bang, it breaks apart, just like it looks like a loaf of bread. And that sort of thermal expansion contraction creates breaks in rocks as well. Well, the last one is responsible for creating structures like this. This is a dome in Colorado. There are other domes like this one that you're familiar with. This is Half Dome in Yosemite National Park. This is another dome in California. It doesn't have to just be California, but this one really shows best what's going on. See, this piece of granite formed way down, it cooled way down deep in the earth. And it was magma that cooled and solidified, but was well insulated. And there were lots, thousands of feet of rock, maybe miles of Earth's crust sitting on top of it. But then in this part of California, the mountain range was pushed up by plate tectonics. And as it was pushed up, this rock, was pushed to a place that it was no longer comfortable, that it was not used to. It was pushed to the surface. And there were no longer confining and overlying layers of rock holding it in place. Rather, as it was pushed up, it was then free to expand because the pressure that had been on it and around it had been released. And in response to that, it cracked. And in these sheets of rock sort of peeling up, exfoliating, like layers of an onion peeling off as that pressure was released and creates the rock that you see here. So that last term, pressure release fracture, is what has gone on to make this rock look like this. Okay? So those are the forces of mechanical weathering and some images that go along with them. I also want to talk a little bit about chemical weathering. Now, of course, they're going to occur at the same time, but chemical weathering usually involves three chemicals. Oxygen, water, and carbon dioxide are the big three. And the first kind of weathering I'm going to talk about is oxidation. Of course, we think about oxidation, we think about rusty vehicles. Well, this is kind of a rusty vehicle. You can see right here, in fact, there's not even a fender left there. We see rust along the floorboards. But really, I thought the one that kind of takes the cake for me is this one here. It's like, dang, that old Grand Am, it's rusted right through its outer skin here. And we could probably take some pictures on the roads around here of rusty cars that are still on the road. But really, this is oxidation. It's the same thing that made hematite put that red-brown streak on that streak plate. It's a combination of oxygen and a mineral, in this case iron, to create an oxide. It doesn't happen just with iron, but sure is a good example of it, rusty cars. Another one would be dissolution. And if I go to your notes right here, there's this formula that I gave you. So basically dissolution, no, it's not dissolution because the rocks can't be disillusioned. I don't think anyway, I've never talked to one recently. No, this is dissolution. So this is basically dissolving a rock. And it might be dissolved in water or basically an acid. That's what these two molecules represent here. Hydrogen or hydroxide would be a base. This would be an acid. This would be a base. And they would tear the mineral apart. And really water can act like an acid as well. The deal is when this happens, this is reversible and you really don't get any new minerals created. And here's the example. So in nature we have this molecule right here, which is water. We have carbon dioxide, CO2, which is what we breathe out. And if you combine those two, you have the most common naturally occurring acid is carbonic acid, H2CO3. That's this molecule right here, carbonic acid. But it doesn't hang around long. It breaks down pretty quickly. It loses a hydrogen right here and leaves us with this molecule, which is bicarbonate. Okay? And this bicarbonate then acts as a buffer. So in nature, these two molecules, water and carbon dioxide, combine to form carbonic acid. It doesn't hang around long, though. It loses this hydrogen and leaves behind this molecule called bicarbonate. Okay, but whenever you see a free hydrogen ion, it's an ion because there's a plus sign by it. Okay, whenever you see that, that's a way to represent an acid. So this is carbonic acid doing its work. Okay, so this is one equation right here. So if we go on the other side of this and sign right here, I want to look at what that acid does. So here's the mineral calcite, calcium carbonate. This is the mineral, this is what's in calcite, that mineral that you had to identify. It's the one that fizzed when you put acid on it. Well, in nature, acid gets on them as well. And when acid combines with calcium carbonate, it can free calcium and release bicarbonate. And you know this can happen because in the real world, if you look at sinks, right here is that happening. This is the calcite mineral, the calcium, getting deposited as limescale After calcite has been carried along to this spot in water, the water evaporated away and it deposited the calcium there as limescale, or here you see it here on a shower head. I think that's the last one I had. Yeah. So that's limescale. So really what's going on here is this acid, the hydrogen ion from the carbonic acid, has worked on the mineral calcite. It has freed calcium, right here is that freed calcium, and created this bicarbonate mineral. But the issue is this calcium, this free calcium mineral right here, ends up being the limescale that we see on our bathroom fixtures as the water that is carrying it evaporates away. So that's what that reaction, that's what that equation is. Water plus carbon dioxide becomes carbonic acid, the most common naturally occurring acid. That's why I am burdening you with this equation. It doesn't stick around long though. The hydrogen ion breaks off of that molecule or is released from it, leaves a bicarbonate molecule, but that hydrogen atom right there, it acts like an acid and it works on this calcium carbonate, this calcite mineral, and it breaks off the calcium, it frees the calcium, creates a bicarbonate molecule, but really this is what we're emphasizing. The calcium is carried then in water and deposited on your bathroom fixtures when the water that's carrying it evaporates away. Hydrolysis then is the chemical union, the last one is chemical union of water and a molecule, water and a mineral to form a new mineral. This is not reversible. There's some examples I'll have to show you in lab when we meet again a week from Thursday. But basically it's if you remember potassium feldspar, that mineral, if you add water to that and enough time, it's going to turn into a number of things, but one of the things it will turn into is kaolinite. Remember that really white clay mineral that just fell apart in your hands? It really looked a lot like chalk. So that hard pink potassium feldspar plus water can turn into kaolinite if enough time is transpired with some other things. But the issue is you can't take out the water, add the other things into the kaolinite, and remake potassium feldspar. It doesn't happen. That's why I say it's not reversible. Couple of last things. Weathering tends to impact mostly exposed or near surface areas, so that this rock internally wouldn't be weathered as much, but externally it's going to really chip away at the surfaces. So if we take a look at this one piece out of that example here, you can see that it gets progressively rounded right here as weathering forces act on it and round it away into this piece right here. Okay, so that process is called spheroidal weathering. The last piece in your notes, a little bit on sedimentary rocks. They cover 75% of the Earth's surface, but only make up 5% of Earth's crust. So my predecessor used to call them the frosting on the cake. So they're that little bit of surface covering on our Earth's surface, but they don't go very deep, if you will. Sedimentary rocks are a thin veneer on part of Earth's surface. So basically the sedimentary rocks we'll be looking at next Tuesday are made in 4 steps. The first step is the weathering process, and when we get back in lab I'll show you the difference between clay, silt, sand, gravel. Okay, those are the main 3 we're going to look at. I know I put more in your notes, but those are the main ones. And so you create the sediment in weathering, you transport it in step number 2, and you do that either in solution or out of solution. By in solution, it's kind of like that calcium that got carried to the bathroom fixture right here. So that was dissolved in water. It ended up, the water ended up, it'd be a drop, if you can picture a drop of water here, evaporating away gradually and depositing that calcium mineral right here as limescale. If you would take the water carrying this calcium and look at it, you wouldn't see the calcium. is very little bit is carried in each drop of water, but over time enough drops of water evaporate that you get limescale deposited there. That's in solution. And then out of solution is mechanically by wind, water, ice, gravity. We've already talked about that. Okay, so you have to scroll down here. You have to create the sediment here. You have to transport the sediment here. You have to eventually deposit the sediment somewhere. You can't keep, carrying it on forever. Obviously, it's got to get deposited. And when it gets deposited, it may be sorted little into bigger, into bigger, into bigger. Different sizes of sediment sorted into different areas. Just as an aside, the finer the transporting medium, the more well sorted the sediment is. So wind would be the finest transporting medium, finer than water, finer than ice. So it would do the best job of sorting out the sediment by size. Glaciers are the thickest transporting medium, and they don't really do much sorting at all. They just bulldoze everything in front of them. So how well sorted the sediment in a rock is a consideration. That's why it's there. But anyway, the last thing then is lithification. Transformation from that loose sediment that we created here, transported here, deposited here, and then it gets transformed into a rock by three main processes. Either gets compacted, squeezed together by deep burial, cemented together, we'll look at some of that on the field trip, or recrystallized, like halite or calcite minerals that you looked at last time. Okay, so that's the sedimentary rock notes. Again, I'll have some visual things for you to look at when we identify sedimentary rocks a week from Thursday. But that is it for those notes, and I will see you. I'm recording this on Wednesday, so I will see you tomorrow on Thursday for the exam, and have a good day.